The purpose of this video is to provide a primer to the new, compulsory, South African lighting and ventilation standard, due to be published in 2023. Before we start, we need to make sure that everybody understands the role of the SANS 10400 standards in the context of the National Building Regulations. Firstly, these are minimum standards, which are deemed to satisfy the functional requirements of the building regulations, and do not supersede the intent of the regulations themselves. The functional requirements of the regulations are very simple. Regulation Part O, as it relates to this standard, requires only two things for the ventilation system. The first is the functional requirement, which states that rooms must be ventilated such that they can be used safely and as intended. This prescription is in Regulation 01. Regulation 03 relates to the approval of ventilation systems and states that ventilation systems may not be installed without the written approval of the local authority. The standard SANS 10400 Part O is not equivalent to the National Building Regulations. It is a minimum standard, which is deemed to satisfy the regulation's functional requirements, as prescribed in Regulation 01. As such, the regulations don't prescribe the SANS 10400 Part O as the only mandatory compliance route. The regulation maintains that a competent person is responsible for certifying that installations comply with the functional requirements of Regulation 01. Regulation AZ4 gives a competent person some scope to use first principles and other recognized standards and methods as references for acceptance criteria. The responsibility, however, remains with this competent person to achieve and prove compliance with the building regulations. Our hope is that the new SANS 10400-0 will prove a suitable standard for engineers who want to achieve acceptable indoor air quality, together with energy efficiency goals. There has been a paradigm shift in this standard relating to ventilation metrics and methods, in order to better align with international norms. The air changes per hour performance metric has been completely dropped from the new standard. Ventilation rates are now expressed in terms of the number of occupants in the occupied zone. This allows high-volume rooms to be ventilated more efficiently. The ventilation rates, prescribed per room type, as detailed in Table 2, are determined using the additive method. Here, the ventilation portion for occupants and the ventilation portion for the room type are considered separately. You will also see this formula includes for a room air distribution effectiveness factor, which we will discuss in some detail later on. The adoption of the additive ventilation method is probably the most significant change to the standard. It was adopted because the additive method better lends itself to efficiently maintaining air quality in the occupied zone. It means that the building owner or operator do not waste resources ventilating parts of the building which are neither occupied nor burdened with contaminant sources. This is because it takes account of the occupied zone only and scales correctly for high-volume rooms. It considers room and occupant-based contaminant sources separately. In addition, ventilation rates are determined for spaces with adapted and non-adapted occupants differently. In this regard, the volumetric air change rates, or air change per hour, didn't address the functional requirements of Regulation 01 efficiently. Also, the application of air change rates in the previous standard was inconsistent throughout building and occupancy types. We briefly mentioned that room air distribution effectiveness was a factor in determining the prescribed ventilation rates. There's some potential for confusion, as ventilation effectiveness can be defined in a few ways. In order to be consistent with the functional requirements of Regulation 01, as well as major international standards, ventilation effectiveness is defined as the room's average contaminant removal effectiveness. This means that a room with fully mixed flow will achieve an index of 1 or 100%. Some may be more familiar with using the mean age of air to define air change effectiveness. In mixing ventilation regimes, there is a correlation between these different ventilation effectiveness indices. An air change efficiency factor of 50% equates to a contaminant effectiveness of 100%. The ventilation effectiveness in a single space can differ seasonally, and therefore, the worst case should be assumed. It is possible to determine ventilation effectiveness experimentally using tracer decay methods or validated simulation models. If these factors are not available at design stage, a lookup table for common configurations is provided in the standard. It should be noted, however, that the room's distribution effectiveness index is a positive scaling factor, and is therefore the reciprocal of the ventilation effectiveness index, as defined. The new standard also describes acceptable criteria for the recirculation and reuse of room air. This allows recirculated air, which has been adequately treated, to be reused for primary ventilation purposes. In achieving this, it is important to note that fresh air is defined separately from outdoor air. Outdoor air is defined in common terms, while fresh air is defined as any air which is sufficiently free from airborne contaminants and can be used for maintaining the required indoor air quality level. Therefore, extracted air can be treated and reclassified as fresh air according to the limits of the various air contaminant classes defined in the standard. Distinguishing between fresh air and outdoor air allows us to incorporate the application of high-efficiency filters and room air cleaner performance into our designs. What this means is that equivalent clean air delivery rates can be included when achieving prescribed fresh air rates. This could permit reduced outdoor air requirements and thereby reduce energy consumption. This is particularly useful in permitting airborne infection control in healthcare facilities, using the most economical methods available. Again, take note that there are limits of application between the air contamination classes as defined in the standard. Some big changes are also present in describing natural ventilation performance. Equivalent performance criteria for naturally ventilated spaces can now also be found in Table 2. Other natural ventilation criteria are based on best practice guides, such as the CIBC AM10 and the WHO guides. Mixed-mode ventilation systems are now also recognized and defined, following best practice from the CIBC AM13. Quite significantly, natural ventilation and air conditioning may be applied in the same space concurrently. Obviously, this should only be done following the component manufacturer's recommendations. An informative annexure has been included as guidance on commissioning and testing of naturally ventilated systems. There is a work plan in place to expand the section into a standalone standard, incorporating the ISO 12569. Also covered by the standard are methods for validation of naturally ventilated spaces using tracer gas dilution testing. Typical methods employed here would be CO2 decay or passive step-up tests. CO2 sensing can also now be used to drive demand control ventilation for intermittently occupied spaces. Take note, as there are specific rules regarding run-on times and post-occupancy flushing. Performance criteria are now available for naturally ventilated spaces. These criteria are prescribed as indoor carbon dioxide limits, which are based on mass flow balance calculations, using ventilation equivalents in liters per second per person. You might be familiar with the equation shown here. Here, the assumption is made, for most spaces, that the concentration of CO2 in exhaled breath and outdoors is constant, as is the volume flow of a room occupant's breath. It would be a good idea to run through the process by which the minimum outdoor airflow quantities are selected for your designs. A typical room data schedule, supplied by a developer to an engineer, could contain information as represented here. It is not unusual for the engineer to have restrictions placed on the arrangement of the ventilation terminals, and for scant information to be available on occupancy densities or indoor air quality requirements. For our example, we'll assume a waiting room for public transport using the following room size and height. The space will be mechanically ventilated with heating and cooling supplied through the ventilation system, with supply air and extract air registers at ceiling level. We've already been introduced to the equation for calculating the minimum fresh air rate. We can now run through how the various parameters are obtained. Firstly, QT is the resultant fresh air rate we want to calculate in liters per second. For the first term, we need to calculate the product of N and QP. N is the maximum number of people in the room, and QP is the prescribed minimum fresh air rate required per person. If the design occupancy of the space is given by the developer, then that value should be used. In the absence of design occupancy values, the default values presented in Table 2 of the standard can be assumed. The minimum fresh air rate, QP, should be taken from the standard. Shown here is an extract from Table 2 of the standard. The row for transportation waiting rooms is highlighted in yellow. Columns 3 and 4 contain the information we are interested in, with a fresh air rate of 7 liters per second per person, and the default occupancy density of 10 meters squared per person. The given room area of 150 square meters determines an occupancy of 15 people for this space. The product of N and QP is therefore 105 liters per second. This becomes the occupancy portion of the total fresh air requirement. Next, we need to calculate the area portion of the total fresh air requirement. This is the product of the floor area, and QB, the minimum fresh air rate required per square meter. The floor area is already given, and QB is found in Table 2. Back to column 2 of Table 2. In this case, QB is 0.7 liters per second per square meter, and the product of N and QB gives us 105 liters per second. This calculated value is the outdoor air baseline for the space, and represents a baseline ventilation rate for demand control applications. Next, we need to determine the air distribution effectiveness factor. For this, we refer to Table 3 of the standard, and use available design information, such as ventilation type, ventilation arrangement, and air classification requirements. This is an extract of Table 3, detailing some basic ventilation configurations, and their related effectiveness factors. Configuration 2 best matches our example, where we've got a ceiling supply of heated air, which would not reach within 1.4 meters of the floor during worst-case winter scenarios. I understand that better design solutions are available in these cases, however this example is intended to illustrate the impact of limited design choice and suboptimal configuration options. Configuration 2 gives us an effectiveness factor of 1.2, which would be equivalent to an air change efficiency of 80%. This calculation may look complicated to the uninitiated, however. It's quite a simple algorithm. It's merely the sum of the space and the occupancy ventilation portions, factored by the air distribution performance potential. Putting these values through our algorithm gives us a minimum fresh air rate of 252 liters per second. So, now that we've determined the minimum fresh air rate, all that's left is to determine what portion of this 252 liters per second of fresh air must be actual outdoor air, remembering that these are not the same thing. To do that, we need to consider the indoor air quality and contaminant levels of the space in relation to adjacent spaces. Before we can talk about extracted air and its reuse, we need to have a quick discussion around the current air filtration standards used in South Africa. Filtration standards are generally divided between those for general filters and those for aerosol filters. South Africa hasn't yet incorporated a standard for aerosol filters, however, for general filters, the SANS 1424 is an adoption of the EN equivalent, and thereby incorporates the EN 779 standard. The EN 779 has divided general filters into coarse, medium, and fine categories, each of which has its own test methodology and classifications. It's easy to demonstrate the problem with South Africa's current filter selection standards by trying to select a 70% efficient filter. A coarse, G2 filter has an average arrestance of 70%. A medium, M6 filter has an average efficiency range, which also covers 70%. And a fine, F9 filter has a minimum efficiency value of, you guessed it, 70%. Because of the practical disconnect between some of the synthetic dusts used in these standards and real-world atmospheric dusts, these standards and classifications do not provide a solid basis for predicting operational performance. The same is true of ASHRAE's MERV classifications. This can create significant uncertainty when designing for filter performance, and when selecting replacement components, as the discussed filtration classes also don't correlate with factors for respiratory health, which is a chief requirement of the building regulations. This problem was recognized quite some time ago, and therefore the EN 779 standard was removed, and replaced with the ISO 16890 in 2018. The new ISO standard is a complete paradigm shift in filter classification, and the resultant filter classes are not equivalent or comparable to those of the EN 779. Filters are now classified according to their PM10, PM2.5, and PM1 efficiencies. Newer standards for aerosol filters, such as HEPA filters, are also available, however the EN 1822 is still valid and appropriate. This image is drawn to scale and represents the comparative sizes of PM2.5 and PM1 particles in relation to the obligatory diameter of a human hair.
The author acknowledges that this is a terrible comparison, as the diameter of the human hair can vary significantly.
The point I wanted to make is, in relation to respiratory health, PM10 particles are typically trapped in the nose, while PM2.5 particles and smaller can penetrate into the bronchioles. The PM1 category of particles, which includes combustion products and viruses, can penetrate to alveoli. With this understanding, the ISO 16890 is a useful standard for designing around required indoor air quality levels. A designer can use this to determine the exact filtration efficiency required for specific pollutants and for respiratory health. I'm sure we don't need to elaborate on why we would want to recirculate room air, but for consistency, and the few that might be new to the topic, it could be useful to confirm here that a conditioned space, maintained at 22 degrees Celsius, could realize an energy cost reduction of around 80%, with the simple limited application of recirculation and reuse of conditioned air. Permitting recirculation makes more capital available for building operation, like maintenance and upgrades. The recirculation of room air can, however, result in lower indoor air quality if overspecified. There are also some restrictions on recirculating certain air contamination classes. Table 4 of the standard defines the health, safety, and sensory irritation classifications for room air, and prescribes permissions and prohibitions on its recirculation and reuse. Here, we have defined 4 categories, from air with low contaminant concentrations, to air with contaminants at concentrations which are potentially dangerous to health or safety. 3 reuse options are described, as well as limitations on treatment and reclassification. Finally, we can get back to our case study of the transport waiting area. I'd imagine we'd all agree that the classification for the air in this space should be low contaminant concentrations, with low hazards, under normal operating conditions. Therefore, Table 4 permits us to recirculate our extracted air within the originating room. It also permits a level of carryover between the exhaust and supply air streams of any energy recovery equipment. It allows extract air to be transferred directly to other spaces of equivalent and higher contaminant categories. Although not really relevant to our case, treatment and reclassification of this air is permitted. This implies that the air can be filtered or purified and reused elsewhere. In summary, extracted air shall be categorized according to Table 4 and Table 2, as applicable. Table 4 allows the treatment and redesignation for recirculation of air on condition contaminants of concern are controlled. This includes both particles and odors. Remember, however, that fresh air may not comprise only treated and recirculated air, but must include a portion of fresh air, not less than that determined by equations 5 and 6 of the standard. Here we have equations 5 and 6. Equation 5 refers to the penetration, or bypass, of an air decontamination system such as filtration. Equation 6 puts a limit on the amount by which the occupancy portion of the fresh air rate, QT, can be reduced. Note that equation 5 uses a ventilation effectiveness factor, which can be substituted with the reciprocal of the distribution factor of Table 3. What these equations do is describe the minimum amount of outdoor air that is required to be mixed into the fresh air when room air is treated and recirculated. Understand that higher ventilation rates may be required to address indoor heat loads and may demand that the supply air quantity greatly exceeds the prescribed fresh air rate. The use of room air cleaners is coming into prominence, and the standard addresses the application of permanently installed devices. It refers to air recirculating units, which employ pollutant removal and destruction technologies, such as particulate filtration and ultraviolet germicidal irradiation, respectively. In order to use such devices within these standards, their independently verified performance must be determined by accredited facilities, such as that at the NIOH. Equation 5 uses the minimum total efficiency of the system for a considered contaminant. However, this can be factored for by using equivalent clean air delivery rates. As with any ventilation system, the room air cleaner's air distribution effectiveness must be factored, as per Table 3. However, the worst cases given in Table 3 would typically apply here. We also know that not all room air cleaner technologies are considered appropriate or safe. You should refer to the excellent ASHRAE monograph on this topic for more. There are several standards available which support the classification and application of room air cleaners. Many of these standards, however, are still under development or in draft. 2 applicable standards are locally under active development within the upcoming SANS 2083 set of standards. ISO and ANSI also have emerging standards, with the AHAM AC01 being the most useful at present. Keep an eye out for the emerging AHAM AC05 standard, which addresses the reduction in viability of microbial air contaminants. By contrast, the older AC01 standard doesn't consider the viability of airborne contaminants. The new SANS 10400 standard deals with exhaust air systems comprehensively. In total, there are nearly 35 clauses and subclauses dealing with the matter. Some highlights from the section include: Local exhaust ventilation systems shall achieve a room average contaminant removal effectiveness of greater than 1. Contaminated exhaust air should be discharged outside of the building's roof recirculation region. Contaminated air should be discharged in a way that prevents entrainment into the leeward recirculation zone of a building. Contaminated air should only be discharged in a way that prevents entrainment into the building's leeward recirculation zone. It should also not be discharged towards any potentially occupied zones. This applies especially to the trafficable areas within equipment and plant rooms. The vertical discharge of air containing airborne hazardous biological agents should be at least 14 meters per second. These zone types are defined in this standard, but for more information, you should refer to the Industrial Hygienist's Ventilation Manual. It is now explicitly permitted for extraction systems to be interconnected with lighting, but only if run-on times are no less than that determined by equation 3. Any extraction system developed in terms of this equation would obtain an approximately 90% reduction in airborne contaminants between when the room is vacated and when the fan is automatically turned off. This is to ensure that sufficient residual contaminants and moisture are removed from the room, so that a damp or moldy environment does not develop. Extraction systems serving residential bathrooms, smaller than 8 square meters, no longer require a rational design, assuming the prescribed minimum ventilation capacity is met. This slide is a bit of a diversion, as it relates to the standard in the context of airborne diseases such as COVID and tuberculosis. The standard alludes to the fact that the safe discharge of contaminated exhaust air is possible, where there is sufficient separation from ventilation inlets and the discharge is not into an occupied area. The standard also describes methodologies for filtration of recirculated air. In the context of filtration levels for COVID, you could refer to guidance from the WHO and RAVA, etc., for the suitability of F8 or EPM1 80% filters for general settings. This is not much different from what would normally be recommended to keep interior spaces visibly clean of environmental dust. Some more good news is that the standard now encourages the use of demand control ventilation to adjust the occupancy portion of the outdoor air intake rates as occupancy conditions change. This was not previously permitted. There are naturally some limits to the application. The control only applies to the occupancy fresh air portion, while the prescribed minimum fresh air rate per square meter must be maintained. Demand control ventilation is also only permitted in spaces of air contaminant categories 2 or 1. The standard dictates that natural ventilation apertures must be either manually or automatically controllable. The thinking behind this is that, where room occupants are given opportunities to control their own environment, they tend to utilize natural ventilation more frequently than artificial ventilation. If ventilation control is taken away, and the occupants are dissatisfied with thermal comfort levels, you frequently find ventilation apertures having been blocked or sabotaged. Offering controllable apertures gives occupants options beyond permanently impairing openings. The minimum natural ventilation aperture sizes and the rules for rooms adjoining courtyards have been clarified, as these were previously reported to be ambiguous. There are now also firmer rules guiding the architectural layout of natural ventilation apertures. To improve the performance of naturally ventilated rooms, the room's dimensions are limited in depth. Limiting the distance between any point in the occupied zone of a room and the nearest ventilation aperture to less than 2.5 times the floor-to-ceiling height can limit air stagnancy. This prescript would typically limit the depth of rooms with single-sided natural ventilation to 6.75 meters, and to 13.5 meters for rooms with cross-ventilation or central ventilation stacks. There's a new requirement specifically for naturally ventilated rooms with heights exceeding 3.5 meters. The standard prescribes the inclusion of high and low ventilation apertures above and below the neutral pressure plane. This inclusion will promote stack effect ventilation and prevent stagnancy in the occupied zone. You can see the neutral pressure plane in this diagram between the upper and lower apertures. On the right, you can see the gradient difference between indoor-outdoor pressures arising from the temperature difference. This pressure differential drives the circulation of air in this space. The position of the pressure plane is dependent on the ratio between the sizes of these apertures. This effect can be used to balance the air flow between spaces in the building, but that is a topic for another day. The standard has a couple of informative annexures. These are provided for information only, and are not mandatory. The first annexure discusses test and balance requirements for natural ventilation systems. It refers to ASTM and ISO standards for tracer gas decay testing using CO2, but suggests that this is not applicable to small shops, residential buildings, non-commercial buildings, and parking garages. The second annexure is intended to raise awareness around the radon risk in South African buildings. Radon gas is dense and can accumulate in low areas of poorly ventilated buildings, especially near current or previous gold or uranium mining activities. Buildings with exposed granite are also at particular risk. The contents of this annexure may be included as a normative section in future editions of the standard, as better data becomes available. This has been a fairly quick summary of the main points of the standard, and the viewer is encouraged to re-watch this overview if there is still uncertainty. The SABS can be approached for further clarification. Public participation in the standards development process is encouraged, and well-motivated contributions, received during the public comment period, will be considered for the final version of this new edition of the standard. Daylighting design is still a weakness and needs contributions from technical experts to improve it further. Domain experts are welcome to join technical committees and working groups.